Hello my friend, welcome back to You Can Do TV channel. The Eppenberg Tunnel is a crucial component of the railway expansion between Olten and Aarau, designed to alleviate the bottleneck on the four-track corridor between Bern and Zurich. The project involves the construction of a twin-track bypass route, as space constraints in the Schönenwert area prevent the addition of two more tracks alongside the existing railway line. The remaining sections, particularly at the tunnel portals, are constructed using cut and cover techniques. Site preparation and excavation. The first phase of the project involved extensive preparatory work, including securing the hillside along a 300-meter stretch with various stabilization techniques. Tunnel boring machine, TBM, operations. The TBM, over 100 meters long, was assembled on site, with the cutting wheel installed in October 2016. The excavation process commenced in January 2017. The TBM utilized a 13-meter diameter cutter head fitted with roller cutters, which operated under high pressure to fracture the rock. Broken rock fragments were transported via a conveyor system within the machine, which was continuously extended as the tunnel progressed. The material was subsequently removed from the tunnel and processed for reuse in concrete production and backfilling. Transition to Hydroshield mode. Midway through the excavation, the TBM encountered water-bearing gravel layers in the western section. To manage groundwater ingress, the machine was converted to Hydroshield mode. A pressurized bentonite suspension was introduced into the excavation chamber to counterbalance water pressure and prevent uncontrolled inflows. During excavation, the TBM advanced using hydraulic thrust, applying up to 20,000 kilonewtons of force through 48 propulsion cylinders. After each 2-meter segment, the machine paused to install a prefabricated tunnel lining ring composed of 6 segments. These segments were initially secured with temporary clamps before interlocking via notches and grooves. The final segment, the keystone, completed each ring, ensuring a structurally stable tunnel lining. A mortar mix was injected behind the lining to secure it against the surrounding rock, while gaps in the upper sections were filled with gravel. The excavated material, mixed with bentonite, was pumped to a separation plant where reusable bentonite was extracted and recirculated. This transition required modifications, including the removal of the conveyor system and excavation buckets, which were ineffective in the saturated conditions. Material processing and logistics. The project incorporated an advanced material recycling system. Excavated rock was sorted based on composition and suitability for construction. Certain geological formations, such as Effingham layers, were reusable for concrete aggregate, while less suitable material was transported for landfill backfilling. A dedicated gravel processing plant was established to handle material on site, reducing the need for transport by truck. The logistics of tunnel construction were further complicated by the constrained worksite, bisected by existing railway tracks and roads. Efficient coordination ensured timely delivery of precast tunnel segments and concrete, despite these logistical challenges. Safety features and finalization. The tunnel includes multiple safety features, including 2 emergency shafts and an escape passage constructed using prefabricated elements. The shafts were sunk using conventional drilling methods, while the passage was built with precast tunnel segments. By mid-2019, the TBM had completed the excavation through various geological formations. The completion of tunnel lining and the transition to railway system installations followed, leading to the eventual integration of the Eppenberg Tunnel into the Swiss rail network, significantly improving capacity and efficiency on this critical corridor. The construction process of crossrail involves an intricate phase of railway system installation after tunneling. The first permanent tracks have been laid, marking significant progress. The focus is now on fitting out tunnels and stations with essential infrastructure. This includes installing track, tunnel ventilation, high voltage power, traction power, signaling, communications, and overhead line equipment. These systems are critical for ensuring safe and efficient operations. Precision and coordination are required to integrate these components seamlessly. Once completed, testing and commissioning will follow to ensure reliability. The goal is to enable TfL-run services through central London and Docklands by December, enhancing transport connectivity across the city. The construction of the Bucharest Metro Line M5 involved transporting and unloading rails for the slab track system. Track construction. The track construction process followed a precise sequence to ensure structural integrity and long-term performance. The first step involved positioning concrete blocks using the embedded block system, EBS, where concrete blocks were carefully arranged to support the rail track. Once positioned, the fastening system was secured to the blocks to provide stability and vibration control. Rail segments were delivered to the construction site and unloaded using specialized equipment to ensure proper handling and positioning. This process was crucial for maintaining alignment and minimizing deviations before installation. Next, track positioning jigs were installed to align and maintain track geometry before concrete casting. A comprehensive pre-casting survey was conducted to verify track alignment, ensuring compliance with design specifications. Once confirmed, fiber-reinforced concrete was poured to anchor the rails and establish a stable track bed. After the concrete set, the positioning jigs were removed, leaving the track in its final embedded state. A total of 15 kilometers of track was constructed using the slab track system, including 5 maintenance lines within the depot. The project also involved the installation of 23 turnouts and 5 double crossovers to facilitate train movement and operational flexibility. Third rail installation. The third rail, essential for powering metro trains, was installed along the entire 15 km stretch of track. Its precise placement ensured efficient power transmission while maintaining safety standards. Project scope and key figures. The project involved constructing a total of 15 kilometers of track, including embedded blocks, and installing 5 pit track lines within the depot. Additionally, 23 turnouts and 5 double crossovers were implemented to enhance operational efficiency. The third rail installation covered the entire 15 km stretch. The construction of an onshore pipeline is a highly coordinated and sequential process, ensuring efficiency. Each stage plays a crucial role in delivering a structurally sound and operational pipeline. The following outlines the key steps involved in the construction process. Stringing. Stringing is the process of distributing the pipe along the designated pipeline route according to the design plan. Each joint of pipe has a predetermined location, ensuring proper alignment and continuity. The stringing crew is responsible for placing each section correctly along the right-of-way, row. Inspectors verify the designated numbers on each joint to confirm their proper sequence. This process is highly efficient, allowing the crew to unload up to 8 joints of pipe in under 10 minutes. Bending. Since the terrain along the row is rarely uniform, pipes must be bent to conform to the topography. The bending process involves inserting the pipe into a specialized bending machine. A mandrel is then backed into the pipe to provide internal support, preventing buckling during the bending process. The operator carefully positions the pipe and executes the required bends. Once completed, the bent pipe is removed and prepared for the next phase. Setup. The setup crew arranges the bent pipes in a manner that facilitates the subsequent beveling and welding operations. Each piece of pipe is positioned strategically, ensuring that welding crews have ample space to work. At each designated start point, a carryback is established, allowing the front-end gang to operate efficiently. Beveling. Beveling is essential for preparing the pipe ends for welding. The process involves inserting a pipe-facing machine, PFM, into the pipe end. The operator anchors the PFM by engaging internal clamping shoes. Once secured, the PFM precisely cuts the pipe end to create the required bevel. Upon completion, the operator retracts the faceplate and moves to the next section. A properly beveled pipe ensures high-quality welds. The main gang. The main gang is responsible for welding the pipeline sections together. The process begins with preheating the pipe to over 100 degrees Celsius, which removes surface moisture and improves weld integrity. The internal welding machine, IWM, is then positioned and prepared for the initial continuous weld, CW, pass. The next pipe section is aligned, and the IWM begins welding. Concurrently, weld shacks are positioned to complete additional weld passes, including hot pass, strengthens the initial weld. First fill, adds material to build up the joint. Last fill, further reinforces the joint. Cap pass, provides the final layer for a secure weld. Once completed, the welded joint undergoes rigorous testing to ensure structural integrity. Ultrasonic testing. To verify weld quality, ultrasonic testing is conducted. A specialized ultrasonic probe scans the weld, detecting any potential defects. The results are available in under 2 minutes, allowing for immediate corrective action if needed. This non-destructive testing method ensures pipeline integrity before proceeding further. Pipe inductance heating and coating. After welding, the joint undergoes preheating through inductance coils, which maintain the correct temperature for coating application. The coating shack, housing the coating head, applies an epoxy mixture to the weld joint. This coating process is completed in less than a minute with minimal waste, ensuring protection against corrosion and environmental factors. Lowering in and backfilling. With welding and coating completed, the pipeline is ready to be placed in the trench. Backhoes and ditchers excavate the ditch along the pipeline route. Side booms equipped with roller slings carefully lift and lower the pipeline into position. These machines work in unison to prevent stress on the pipe and ensure proper alignment within the trench. Once the pipeline is in place, the backfill crew begins burying the pipe. Bulldozers then restore the row, grading the surface to its original condition. This step ensures environmental restoration and stability of the pipeline corridor. The Cardinal Aggregate quarry operates through a structured process to extract and process limestone efficiently. Initially, dirt is stripped to expose the rock, with excavators and haul trucks removing and stockpiling soil for future use. Drilling rigs create 15 to 30 holes for each blast, boring through solid rock at 5 feet per minute. Controlled blasting, conducted under strict safety regulations, yields 15,000 to 25,000 tons of raw aggregate weekly. The extracted rock is transported to the crushing plant, where jaw crushers reduce it to smaller sizes. The processing plant refines the material into multiple products, including road base and construction aggregate. Finally, a state-of-the-art weighing system ensures precise loading, allowing up to 400 trucks to transport materials daily. M-sand, manufactured sand, is a cost-effective and eco-friendly alternative to river sand, widely used in construction. The manufacturing process involves multiple stages to ensure the production of high-quality sand suitable for various applications. The process begins with rock boulders being blasted and broken into smaller pieces at the quarry. These broken rocks are then transported to a dump where dust, mud, and other unwanted particles are washed off using water. The cleaned rocks are then fed into a jaw crusher, which reduces them to a size of approximately 40 millimeters. The 40 millimeter stones are further crushed in a cone crusher, reducing their size to 20 millimeters. These 20 millimeter stones are screened using a vibrating screen, where oversized particles are removed. The remaining stones then pass through a vertical shaft impactor, which crushes them further to a size of 4.75 millimeters while also ensuring a cubical shape. A second round of screening is conducted to separate finer particles. The sand is then processed through a water classifier, where water washing removes any particles below 150 microns as slurry. The final product is clean, high-quality M-sand, ready for use. Dash 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 dash. The Phi South Dakota 225 stone crusher is an efficient solution for repairing cold patch forestry roads. Designed for powerful tractors, 280-400 horsepower, it crushes stones up to 50 centimeters in diameter and reaches a maximum operating depth of 25 centimeters. The process begins with surface ripping and grading, forming two windrows of material. The hydraulic door regulates output size, ensuring uniform crushed material. The integrated hydraulic counterblade can be adjusted from the tractor's cab, optimizing efficiency. Built for durability, the unit features an oversized door, internal hardox protections, and a side scraper system that reduces wear. Adjustable skids and interchangeable protection chains enhance adaptability. Available in 200, 225, and 250 centimeters working widths, it is ideal for processing rocky soils and maintaining unpaved roads. The process begins with a base station setup that supports all connected equipment. A dozer equipped with machine control grades the project, followed by trimming with the millimeter GPS system. Paving is then completed using the same system, ensuring precise alignment and elevation. The elimination of string lines allows for unrestricted access to the site, making material transportation smoother. Additionally, a single operator can use a rover to mark reference points, reducing labor costs. Engineers and inspectors have recognized the efficiency and accuracy of this system, which ultimately leads to faster project completion and lower overall costs. The TopCon millimeter GPS system is revolutionizing concrete paving by eliminating the need for traditional string lines and survey stakes. At Gehring Construction and Ready Mix in Hastings, Nebraska, this system has been utilized for increased efficiency and accuracy. The equipment is fully compatible across different phases of construction, from site grading with a dozer using 3DMC to fine grading with a trimmer and finally paving with the millimeter GPS system. The Gameco GP 2400 concrete slipform paver is a versatile and efficient paving machine designed for precision concrete paving applications. It is available in 2-track or 4-track configurations, allowing contractors to choose the best option for their project needs. The paver features a telescoping frame, capable of extending up to 6 feet (1.83 meters) on the left side, enabling flexible paving widths ranging from 16 feet (4.88 meters) to 24 feet (7.3 meters), with frame inserts. Equipped with G-digital controls, the GP 2400 seamlessly integrates with stringline or 3D machine guidance systems, ensuring accurate and automated slipforming. The T-beam mounting rail provides quick mold positioning and easy installation or removal. The Viaduct, a double-deck concrete highway, had served the city for over 6 decades but was deemed seismically vulnerable. In February, crews began the step-by-step dismantling of the structure, ensuring safety while maintaining traffic flow and protecting surrounding buildings and infrastructure. The process was divided into multiple phases. The first phase began at the Columbia Street on-ramp, where single-deck sections north of Pike Place Market were dismantled. Machines equipped with hydraulic crushing jaws, jackhammers, and concrete saws methodically broke apart the roadway while ensuring underground utilities were protected. Piles of rubble acted as buffers, preventing damage to critical infrastructure, and curtains were used to contain flying debris. Water was continuously sprayed to suppress dust, with all collected water undergoing treatment before disposal. The second phase focused on the central waterfront, where demolition crews tackled the double-deck sections of the viaduct. Special care was taken to protect the nearby railroad tracks, requiring precise removal techniques to prevent disruptions to rail operations. Crews worked span by span, ensuring that each section was safely removed before progressing further. As sections were demolished, steel and concrete debris were sorted and sent for recycling. This phase also included dismantling areas near Pike Place Market, where additional precautions were necessary to minimize impact on businesses and pedestrians. In the final phase, demolition efforts shifted to the southern waterfront, where the viaduct ran just inches from adjacent buildings. The work required precision to avoid structural damage to surrounding properties. Despite the proximity challenges, the project maintained uninterrupted pedestrian and vehicle access throughout the process. Streets were reopened as demolition progressed, allowing the city to transition seamlessly into the next stage of waterfront redevelopment. Concluding the demolition, the old ferry walkway was removed and replaced with a modernized structure, symbolizing the transformation of Seattle's waterfront. By September, the last section of the viaduct had been removed, paving the way for an open and revitalized public space. The replacement of the railway bridge over the Abbeg River, located between Buttevant and Charleville train station, was a highly coordinated and time-sensitive engineering project. The operation had to be completed within a 60-hour window over the Irish October bank holiday weekend to minimize disruption to the Dublin-Cork railway line. The old underbridge 313 was a two-span steel structure that had deteriorated significantly, necessitating its replacement with a concrete box culvert structure. The project began with preliminary assessments in 2010, identifying structural weaknesses in the central pier and abutment-bearing plates. Temporary speed restrictions were imposed until the full replacement could be executed. Despite these challenges, the work proceeded on schedule. At 22:30 on October 28, possession of the railway line was granted and the removal process commenced. The track was dismantled, the existing bridge was cut and lifted out, and extensive excavation was performed to create a solid foundation for the new culverts. Culvert installation involved placing 84 precast units, each weighing 30 tons, in a meticulously timed sequence. Heavy-duty cranes operated on both sides of the railway, lifting and positioning the components within a strict 17-minute time frame per unit. The culverts were then covered with ballast retainers and retaining walls to reinforce the embankments and riverbanks. Track reinstatement was completed efficiently, with ballast placed and compacted in layers. Irish Rail took over the site for final track laying nearly a full day ahead of schedule. The railway line was restored to full operational status within 40 hours, allowing trains to resume normal service at speeds of up to 90 miles per hour. This successful bridge replacement ensured the long-term safety and efficiency of the critical Dublin-Cork rail corridor. The construction of a Geogrid reinforced bridge abutment enables rapid and efficient bridge completion within just 80 days. This method was successfully implemented on the A3 freeway in Germany, where a 36.60-meter-long bridge was built according to DIN and 1991 standards. The process involved simultaneous construction of the superstructure and abutment, significantly reducing road closure durations. The abutment was constructed using a layer-by-layer technique with biaxial 4-track MDT Geogrid, PVA, offering 400/400ths of a kilonewton per meter tensile strength. Light construction equipment facilitated efficient compaction within a confined space. Measurement instruments, including displacement transducers, earth pressure cells, and inclinometers, were installed to monitor structural performance. Gabions and concrete panels provided both aesthetic and protective functions. The pre-assembled 400-ton composite bridge was placed precisely, minimizing on-site delays. With only 2 full road closures required, this approach ensured a fast, safe, and architecturally appealing result. The hydraulic cement concrete paving process involves multiple precise steps to ensure durability, smoothness, and longevity. The process begins with surface preparation, where the existing pavement is shot blasted to remove oil, debris, and any loose material. This step roughens the surface, improving adhesion for the new concrete overlay. Once the surface is ready, concrete is delivered from the batching plant and transferred onto a conveyor belt, which deposits it in front of the paving equipment. The first machine in the sequence is a spreader, ensuring an even distribution of concrete across the width of the pavement. This is followed by a paving machine that consolidates the material and ensures the required thickness and cross-section are achieved. A curing compound is then applied to retain moisture, promoting proper hydration and strength development. Simultaneously, small grooves are raked into the surface to enhance traction and improve water drainage, making the road safer for vehicles. The entire operation is guided by a global positioning system, which ensures precise alignment and thickness control. This modernized paving approach results in a smoother ride, reduces maintenance needs, and extends pavement life, making it a cost-effective alternative for long-term road infrastructure projects. The process begins with earthworks, where millions of cubic meters of soil are excavated and repurposed for embankments, noise barriers, and landscaping. A network of temporary haul roads ensures efficient material transport while minimizing disruption to local communities. This construction project is a monumental infrastructure project aimed at revolutionizing high-speed rail travel in Britain. Spanning 140 miles from London to the West Midlands, the project involves extensive engineering works, including tunnels, viaducts, bridges, embankments, and cuttings. Tunneling operations are a significant aspect of the project. Several tunnel boring machines, TBMs, are deployed to carve out underground passages, such as the Chiltern Tunnel and Northolt Tunnel. TBMs like Florence, Cecilia, Emily, and Anne progress through miles of rock and clay, installing tunnel linings and cross passages as they advance. Viaducts and bridges form another essential component of HS2's infrastructure. The Colne Valley Viaduct, set to be Britain's longest rail bridge, is being assembled using prefabricated deck segments and iconic V-shaped piers. Other structures, like the Wendover Dean Viaduct and Tame Valley Viaduct, feature innovative low-carbon and off-site manufacturing techniques. Major station developments include Old Oak Common, the UK's largest new build station, and interchange station in Solihull. Both incorporate sustainable designs and seamless integration with existing transport networks. Rail system installations will commence in 2024, involving track laying, power supply, signaling, and telecommunications. These systems will ensure high-speed and reliable train operations, marking a transition from civil construction to an operational railway network. The construction of the NBS Wendling and Ulm, LOS 4-6, has reached a major milestone with the completion of the final RE 330 contact wire installation in section GU4. This marks the final phase of electrification on the high-speed railway from Hohenstadt to Ulm. A total of 80 kilometers of catenary system was successfully installed along the route. The project utilized specialized equipment, including the ZEC assembly unit, to ensure precise and efficient installation. This process is crucial for providing a reliable power supply to high-speed trains operating on the Stuttgart 21 project. The final contact wire was mounted in August, marking the completion of the electrification work in this section. This achievement represents a key step in the overall progress of the new railway line, which aims to improve transportation efficiency and connectivity between major cities. With this milestone, the NBS Wendling and Ulm is closer to full operational readiness, bringing modern and high-speed rail travel one step closer to reality. Process of operation. The work begins with the positioning of the P190 train on the designated track section. The machine's compact length allows for easy shunting and efficient worksite preparation. The track renewal train is equipped with sleeper wagons, which hold new sleepers that will replace the old ones. The first step in the renewal process is the removal of old track components. The machine facilitates the loosening of fastening systems using its automatic fastening release system. This allows for a systematic removal of the rails and sleepers without manual intervention, enhancing efficiency and worker safety. The P190 utilizes gantries that run on dedicated rails mounted on the sleeper transport wagons and the track renewal train itself. These gantries play a crucial role in transferring new sleepers from storage wagons to the track. The number of gantries used depends on the project size, with 2 gantries recommended for operations involving 8 to 10 wagons. The old sleepers are removed systematically, making way for the new ones, which are placed with precision to maintain the correct track alignment. Once the new sleepers are in place, the rails are laid on top. Advanced clamping and fastening systems ensure proper alignment and secure placement of the rails. The automatic fastening release mechanism enhances this step by providing a seamless attachment of rails to the new sleepers. The track renewal process also involves ballast management to stabilize the newly installed sleepers and rails. Excess ballast is removed using specialized equipment integrated into the track renewal train. The alignment of the track is carefully monitored to ensure it retains its initial geometry. The Matisse P190 offers optional auxiliary wagons to enhance efficiency and functionality. WCA wagon provides additional workstations for loosening small materials, magnetic drums with conveyors for efficient material handling, gantry stowage for transit, and an adjustable running rail for gantries. It can also include a diesel hydraulic group to provide extra traction force and small material storage facilities. The Matisse P190 track renewal train is a specialized machine designed for small to medium-sized railway track renewal projects. Despite its compact size, it incorporates advanced technology and efficient automation to ensure precise and reliable track replacement. The machine follows a systematic process that enhances productivity, safety, and accuracy while maintaining the existing track geometry. WMM wagon, used for pre-renewal tasks such as track measuring and excess ballast removal. Additionally, it serves as a storage space, workshop, social compartment, or generator integration unit to provide extra power during operations. After track renewal is complete, a final inspection is conducted to verify the accuracy of the installation. The measurement systems in the WMM wagon can assess track parameters to ensure compliance with required specifications. Once approved, the track is ready for further maintenance and eventual use. The Matisa P190 is an advanced yet compact track renewal train designed to maintain efficiency, safety, and high-quality track alignment. Its automated processes, modular design, and flexibility make it a valuable asset in railway infrastructure projects. Constructing a bridge under an active railway line is a highly intricate engineering process that requires meticulous planning, strict adherence to safety protocols, and advanced construction techniques. In the United Kingdom, railway bridge construction projects are subject to rigorous regulations and oversight by Network Rail to ensure minimal disruption to rail services while maintaining the highest safety standards. The process typically begins with a site assessment and feasibility study. Engineers conduct geological and hydrological surveys to evaluate soil composition, ground stability, and potential environmental impacts. These assessments help determine the type of bridge foundation required and identify any challenges related to underground utilities, existing infrastructure, or nearby structures. Additionally, railway traffic patterns are analyzed to schedule construction activities with minimal interference to train operations. Following the initial assessment, the design and engineering phase takes place. Engineers develop detailed bridge designs that accommodate the railway load above while ensuring the longevity of the structure below. Key design considerations include load-bearing capacity, material selection, and impact resistance. In the case of the Alderley Edge Railway Bridge, a 30-meter span bridge was constructed to allow the railway to pass over the new bypass. The design needed to ensure the bridge could handle the heavy and dynamic loads imposed by trains, while also providing sufficient clearance for vehicular traffic beneath. Once the design is finalized, regulatory approvals and coordination with Network Rail and local authorities are necessary. This involves securing permissions, obtaining safety certifications, and preparing contingency plans for potential disruptions. In the UK, railway bridge projects must comply with Network Rail's stringent safety standards and environmental regulations. Given that railway lines are critical transport arteries, coordination with stakeholders is essential to schedule temporary closures, speed restrictions, or alternative routes if necessary. Construction phase. The construction phase involves several key steps, starting with site preparation and foundation work. Excavation is performed to create space for bridge supports, while deep foundations such as piles or caissons are installed to stabilize the structure. In cases where railway operations must continue uninterrupted, engineers often use techniques like jacking or sliding prefabricated bridge components into place. For the substructure and superstructure construction, reinforced concrete or steel beams are typically used to create a strong support system. In many cases, Modular bridge components are pre-assembled off-site and then transported to the location, minimizing disruption to railway traffic. In the case of the Alderley Edge Bridge, pre-stressed concrete beams were likely utilized to provide durability and reduce on-site construction time. Throughout construction, continuous safety monitoring is performed to ensure both railway stability and worker safety. Sensors and automated monitoring systems track vibrations, ground movements, and structural integrity in real time. Any anomalies trigger immediate intervention to prevent potential failures. Once the bridge structure is completed, the project enters the inspection and commissioning phase. Engineers conduct thorough load testing to verify the bridge's ability to withstand railway and road traffic. Once the bridge meets all safety and performance standards, it is officially opened for public use. In the case of the Alderley Edge Bypass, the bridge was a crucial component in the £52 million project that improved traffic flow in Cheshire while ensuring uninterrupted railway operations. The bridge under railway construction industry in the UK. The UK has a well-developed railway infrastructure with over 40,000 bridges and tunnels under Network Rail's management. Many of these structures require ongoing maintenance, replacements, or upgrades to accommodate increasing rail traffic and evolving transport needs. The railway bridge construction industry plays a vital role in ensuring the safety and efficiency of the network. In recent years, Network Rail has undertaken several ambitious projects to replace or reinforce railway bridges. A key example is the Ordsall Cord in Manchester, a £320 million project that included the construction of new railway bridges and the enhancement of existing structures. The project utilized innovative construction techniques, including prefabricated bridge sections and high-strength steel components. Another major project is the Warrington grade separation near Peterborough, where a new underpass was constructed beneath the East Coast Main Line to allow freight trains to pass without disrupting passenger services. This project, completed in 2021, involved a groundbreaking box-jacking technique, in which a 155-meter-long concrete structure was pushed into place beneath an active railway in just 9 days. The funding and costs associated with railway bridge projects vary depending on complexity, materials, and location. Smaller bridge replacements can cost between £5 million and £20 million, while larger-scale projects like the Warrington grade separation can exceed £200 million.